Hello, this is John Black again. It's like the seventh time I've done this movie. God, I hope it doesn't erase again. Anyways, let's review the last time. We were saying how if you go 5 miles west, or 5 miles east rather, uh, that's the best you can go in that dimension. But let's say you go 5 miles and you divert some of your direction into another dimension like north, that you have to take away from the first dimension going east. So if you go 5 miles, you're not going to go 5 miles east if you divert some of your direction into the northern dimension, right? It's the same way with time, though. Time is just a spatial dimension. Don't think of it as temporal. Uh, it has, just like up and down, and north has south, east has west. Um, Time, it has forward and backwards. You know what I mean? It is a dimension. Um, so if you move through the time dimension and you're just standing still, that's the fastest you can go through that dimension. Just like if you go east and that's the only dimension you go, that's the fastest you will go. You will go the furthest east that you can go. But if you start diverting your uh, direction into another dimension, you know what I mean? You're just standing there and you're going through time. Now all of a sudden you start going north. That's a different dimension than time. So you're going to divert some of your direction away from the time. And the only way you can do that is by slowing time down. Okay? That's what I mean by time bubble. Everyone that is moving at a different velocity is actually in a different time bubble and everything that moves with them. So if you're on a spaceship, it's not just you in a time bubble. The spaceship's moving as fast as you and everything in it. So everything in there, your heart, your rate of thinking, everything, your clocks, electrons, they all move at that slower rate. All right. And I want you to think about this picture over here. I got a running guy and a still guy. See that? I'm pointing. And the running guy is actually, his clock is running slower. He's in a different time bubble than this guy standing still. This guy standing still is in the same time bubble as Earth because he's standing still relative to Earth. Um, so his clock is the same as everything else on Earth that's standing still, but this clock is moving slower. Okay, and you can't tell because he's not moving, close to the speed of light or anything. You're not going to be able to see it. And the other thing is about this length. Remember the length? Faster you go, the length gets smaller. So when this guy's running, the distance between him and the standing guy is smaller than the distance for this guy. This guy sees, say, 10 feet, right? The still guy. Well, the running guy, he only sees 9 feet, 0.9999999, and keeps saying 9 forever. He only sees that much distance, which is slightly smaller, okay? And we're going to get to this thing called the twin paradox. It's not really a paradox. The scientists all knew the answers at the get-go. But because it sounds so funny that anyone who doesn't know about science, they're like, this is a paradox. And here's where the paradox comes in. See the guy in a spaceship? He's in a constant velocity driving by Earth. He looks out his window. He sees the guy on Earth, okay? The guy on Earth sees the guy in the spaceship. When the guy on Earth sees the guy in the spaceship, his clock is running slower because he's moving faster than the guy on Earth, right? So he'll see the guy moving slow. If he throws something up in the air, the ball will come down slow. He walks in slow motion, just like slowing down a movie. It'd be freaky. But remember, nothing is standing still and nothing is moving. Everything is relative. So this guy here on the spaceship, he is the one, when he looks out at Earth, he thinks he's standing still, and he thinks that the guy on Earth, his clock is moving slow, and he's walking slow and throwing things, and they come down slow. And the other thing is about the length. He sees the Earth shrink like that, but the guy on Earth sees the spaceship shrink like that. Okay? That's where they say there's a paradox, because how can this guy, what if this guy goes around and turns around and comes back? Both clocks were running slower. Who gets older and who gets younger? According to the guy on Earth, he sees this guy's clock running slow, so he should be, he's the guy who's moving, so he should be young because his clock is slowing down. But this guy has the same story. He looks out the window, he sees this guy's clock running slow. He says, when I get back, that guy should be young and I should be older because his clock is running slower. They can't both be right, though, right? I want you to think of something. This next picture here, see this thingy here? Yeah, this guy here, he measures himself. He measures 1, 2, 3 red lines tall. He measures this other guy. 2 red lines tall. Okay? But this green guy over here, he measures himself and he's 3 green lines tall. And he measures the other guy and he says 2 green lines tall. They can't both be 2 and both be 3 lines tall, right? But according to his frame of reference, he's right. This guy is only 2 lines tall. And according to this guy's frame of reference, this guy is right. They both see the other guy is shorter, but they're both correct. It's just about frame of reference. Think of it this way. If you're walking, okay, and you are walking towards another person that's across a football field, he looks smaller to you, doesn't he? Because his frame of reference is not the same as yours. He's so far away. But when he looks at you, you also look smaller. Neither one is true. Neither one of yous are smaller. But from your frame of reference, it looks like yins are. Okay? Because when you get up and meet up in the middle of the field, you both are in the same frame of reference now. You're not 100, 300 feet away or whatever. So you both look like you're the same size, and you realize that when you get there. I'm going to explain how that happens, how one is old, how only one gets old and one gets whatever on the next video when I talk about the twin paradox. But I want you to think about a couple things with this time bubble. Think about the planet Earth, okay? Planet Earth spins on its axis, right? Anything that spins, think about a tire bicycle. When you are on the inner side of the bicycle, it only spins around a couple inches, right? But if you go all the way to the end of the tire, that tire has to spin, you know what I mean, all the way around the tire, which is a lot bigger distance than the inside of the tire. So that's the same with planet Earth. As it spins, the inner part is actually moving fast. No, the outer part is actually moving faster than the inner part. So that means faster moving, the clock is moving slower on the outside of the Earth than it is on the inside. And that means that there's a couple years difference between the age of the inside of the Earth and the outside. The outside has a slower clock. It's younger. The inside of the Earth is older by, like, say, 3 years than the outside, than the crust. It's the same with the galaxies. If you think of a galaxy, you have a black hole in the center. Everything revolves around that black hole. And like I'm saying, anyone who's in a different velocity is in a different frame of reference, and that means their clock is moving slower or faster compared to someone else moving at a different velocity. Now, if you're let's say you're 1,000 miles away from someone, or a million, whatever. If you're both moving at the same velocity, you're still in the same time bubble. Now, the space in between you and things in between you that are moving at different velocities, they're in a different frame of reference, a different time bubble. But you can be in the same time bubble and be away from each other distant-wise and still be in the same time bubble. You know what I mean? Your clocks will be running at the same time. Anyway, I think that's about enough for this one. We're going to talk about the twin paradox next time, about how this guy goes to another planet, say another star, and then comes back. Who is actually older and who's actually younger and why? Okay?